Welcome to Swindon New College's Maths Department. My name is Kevin Lister and I'm the Programme Leader for A-Level and Further Maths. And what I want to do in the next 10-15 minutes is give you a flavour for the A-Level and Further Maths classes. And to do that, I'm going to be teaching something called the Mandelbrot Set, which is a relatively new piece of maths. It was only sort of discovered about 40-50 years ago. But what's extraordinary about it is that we can do virtually everything that we need in the Mandelbrot set just with basic maths that you've already seen in year 7 and year 8. What I also want to do is just show you how we deliver our classes in New College. So we deliver all the classes through Teams, with half the class at home online and half the class in the class. We deliver the teaching using OneNote, so that those students at home can get immediate access to the class notes, and all the class notes are saved permanently online. All the homeworks are issued through OneNote. All the homeworks are submitted by the students using OneNote, and likewise the tests as well. So without any further ado, let me share the screen and I'll go to OneNote and we'll start talking about the Mandelbrot set. And this is the Mandelbrot set here, this extraordinary, complex and beautiful pattern. And what we find is that we can zoom in on any particular area. So this area here might be the Mandelbrot, might be an enlargement. And we can zoom down in any particular area. And what we find is increasingly complex patterns as we zoom in on this border area between the black part and this dark blue area on the outside. And in fact, if you look really closely in this little leg coming off down here, you'll see another smaller copy of the Mandelbrot set, and this entire pattern will be buried within this smaller copy, and then we'll find an infinite number of smaller copies in this area as we keep zooming on down. Now, your initial thought when you look at this is that this must be extremely complex maths to try and develop and generate a picture of this beauty and complexity. And in fact, the maths behind this is extremely simple, and the pattern really just relies on maths that you have seen in year 7, year 8, and year 9. And with the help of a little bit of work from Further Maths, it brings that all together to create this extraordinary, beautiful pattern. So to do this, we're going to think about some basic maths that we've already seen. We're going to start with a number line. So the black line is a number line. I start with 0, 1, 2, 3, 4, and I go back the way. 0, minus 1, minus 2, minus 3, minus 4. Now, if I'm at 2 and I multiply by 2, I come to 4. So I'm at 2 and I add one lot of 2 to get to 4. So in total, I've now got 2 lots of 2 here. But if I'm at 2 and I multiply by minus 2, I come to minus 4, and that should be a minus 4 there. Now, the minus 4 now means I'm going along 1, 2, 3, whereas before, when I went from left to right, I only went along one lot of 2. So there's something asymmetrical about the multiplication operation on the number line. So let's have a think about how we can resolve that asymmetry. And to do that, what we do is quite simple. We have another number line that goes up at right angles to the number line that we've seen so far. And we're going to call this the imaginary line. So this number line up here is our imaginary axis. And once we've got that, then everything else starts getting really easy. So if I'm at 1 and I want to multiply by I, 1 times 1 lot of I is just I. So if I'm at 1 and I multiply by I go to 1 lot of I, which is up here. So I've rotated round through 90 degrees. Likewise, if I'm at I, and I multiply by I again, I'm going to rotate round through 90 degrees again. So I times I is I squared, and I squared has taken me to -1. Now that's really cool because I can take the square root on both sides. The square root of I squared is just I, and that must be then the square root of -1. So I is the square root of -1. And we get this remarkable idea by virtue of thinking of our multiplication by I as a rotation of 90 degrees. Okay, I can continue on. If I am at -1, which we know is I squared, I can then multiply by I to get -I. So -1 times I will get me another 90-degree rotation to this point down here. If I'm at -I and I multiply by I again, then I get -I squared. Well, I squared we've already decided is -1. So I've got -1, which is +1. So multiplying by I again is taking me back to my starting point. So each time I've multiplied by I, I've had a 90-degree rotation. And this is completely symmetrical now. I've got a nice circle here. Unfortunately, that line's not a great arc, but I've got a nice circle going around where each operation is exactly the same scale and size on the diagram. Okay, now that makes life quite interesting for us because I can now address any point on this plane in terms of where I go on the real axis and where I go on this new imaginary axis. So this point up here, for example, might be 1 plus 2 lots of I. So I'm going along 1 on the real axis. I'm going up 2 lots of I on the imaginary axis. I might be over here as well, and along over here. So this point would be 3 on the real axis plus 1I on the imaginary axis. And then anything on this plane which I address like this, I'm going to call it Z. So this might be Z1 and this might be Z2. And you can see now straight off all the normal stuff that you've already seen in terms of adding like terms is going to apply. So Z1 plus Z2 is going to be 1 plus 2I plus 3 plus I. So we get 4 plus 3I. If I can multiply terms, I can probably, if I can add terms, I can probably multiply them. So Z1 plus Z2. Let's change the addition to multiplication, Z1 times Z2. So that's now going to be 1 plus 2I times 3 plus I. And we can just apply the FOIL that we've already seen. 1 times 3 is 3. 1 times I is I. 2 times 3 is 6. So I've got 6I here. 2I times I is 2 lots of I squared. I squared we know is -1. -1 times 2 is -2. -2 plus 3 is 1. And then we can add the like terms together here. I get I plus 6I is 7I. Okay, so what else can we do? Well, the other thing we can do is we can get distances. So Z1 was equal, that's an equal sign there. Let's just make that a little bit clearer. So we can get distances. So for example, if I wanted the distance between the origin and a point over here, I can just use Pythagoras. I've got a right angle triangle down there. So I can use this symbol for the distance, which is the modulus, and it's going to be 1 squared plus 2 squared, which is 4 plus 1, which is the square root of 5. Okay, so again, everything that you've seen so far is just all the stuff that you've seen through your career in maths so far. Adding like terms, that's kind of year 7 stuff. Expanding out brackets, year 8 stuff, and a bit of Pythagoras, year 9 stuff. So nothing at all too frightening. And that is basically pretty much all we need to find these extraordinary patterns. The only thing that we need to do now is just a little bit more notation, and we're going to write down the equation to get the patterns that we started with at the beginning. And the equation for the pattern is this. It's Zn plus 1 is equal to Zn squared plus C. And C is some value on the plane. So in this first case here, for example, C might be 1 plus 2, or C might be 3 plus I. So what we do now is we say, well, let's start with n being equal to 0. And that means that if the n is 0 here, the first value is Z1 is Z0 squared plus C. And C we can take as any value on the plane. And we might say C is, for example, 1 plus I. Just using easy numbers just to demonstrate. So I've got 1 plus I. And we start off with Z0 equals 0 plus 0I. Now, what happens now? Well, this is now 0. So that means that Z1 is 1 plus I. Now, the n increases from 0 to 1. Which means that the second term, Z2, is Z1, so the n is now 1, squared plus my C value, and this is C, and C is equal to 1 plus I. So we take our value of Z1 and put it into the equation. So I got 1 plus I squared plus 1 plus I. Scroll down and we're going to expand this term out here. 1 plus I squared is 1 plus I times 1 plus I plus 1 plus I. So we can multiply this bit out and then add this. So 1 times 1 is 1. 1I plus another I is going to be 2 lots of I. Then I've got I times I, which is I squared, plus 1 plus I. We know that I squared is minus 1, so that minus 1 and that one can cancel. Then I've got 2I plus I, which is 3 lots of I, and then I've got 1. Okay, and then we can do the same again. We can say n equals 2, which means that the third term is equal to the second term squared plus our C value, which in this case we said is 1 plus I. This value goes back into our equation, and then we can then repeat the process again. Okay, so let's just follow the path of what's happened. So this value went into here, and then this value goes into here, and then the process continues. Okay, so what else can we do? Well, we also know how to find distances, and so we can get the distance. So we can find the distance of Z1 from the origin from Pythagoras, 1 squared plus 1 squared, which is equal to the square root of 2. Then we can come to Z2. We can find the distance of Z2 from the origin, which is the square root of 1 squared plus 3 squared, which is the square root of 10. And that is basically all that we need to do to get this Mandelbrot set. And what we do is we continue on this sequence. The sequence continues on, and we just put a condition. We say that if we start at some point C, and that we exceed, say, a given length, say we exceed a length of, say, 200 in 4 iterations, then we would colour that particular point that's referred to by the C, say blue. And if it takes, say, 20 terms to exceed the same point, then we might colour it red. And that's it. That's basically all that we need to do. So let's go back up to the pattern at the top and let's just see exactly how this works. So what we've got up here, let's go for a red pen, is we have our real axis which runs along this line along here. And the imaginary axis that we've just introduced runs somewhere around about here. And if we take a point, say, in this area, what we find is that the distance, after a few iterations, doesn't move and doesn't change. So we go iteration after iteration after iteration, and the distance remains the same. So in this area, for example, our C value might be fairly small, might be, say, 0.1 plus 0.1 I. So after 100 iterations, we'll find that the distance is not changing. Whereas if we go outside over here, we'll find perhaps our C value might be, say, something like 3 plus 3I. And what we'll find is just after a couple of iterations, the distance will have gone off to many millions. What we find is that in this border between the area where the distance doesn't increase and the distance does increase, we have this incredibly complex pattern. One place, say here, and the distance from the origin after iteration doesn't change, but we can be just somewhere ever so slightly outside and the distance does change. The distance goes off and diverges off to infinity. And over here, we might get a different rate of divergence. So the color of each pixel just represents the rate that the value or that the distance diverges away from the origin as we iterate through the cycle of calculations that we just showed earlier on. It's an extraordinarily simple bit of maths. It uses this idea of complex numbers that we'll see in further maths. And it really just brings together so many parts of maths into something that's really quite unexpectedly beautiful. And not only is the Mandelbrot set beautiful, but it has profound implications as well in terms of what we can calculate and what we can't calculate. So if we're somewhere in this area, we can calculate what the distance is likely to be. If we're somewhere outside, we can calculate what the difference is likely to be. If we're somewhere in this complex area, this boundary area, then the slightest change to our input has a profound change to our output. So up to now, all the maths that you have been doing has been along the lines that you are given a problem, you're given some numbers to put into the problem, and you find the answer. What this is showing actually is that there's certain areas of maths where you can have a problem, you can put an answer into the problem, but you can't actually predict what value is going to come out. So suddenly all your maths rapidly changes and goes head over heels. So I hope that's been interesting. I hope it's given you a bit of a flavour for how we can deliver the A-level and further maths course. We're really excited about the use of Microsoft OneNote. It's a great teaching platform. It allows an enormous opportunities to exchange data and to exchange ideas between the staff and the students and between the students themselves. So we hope to see you next year. Thank you very much.